Welcome back to All the Math. That's all the math you need for computer science. This is my favorite episode of the entire linear algebra volume, and this is about applications, okay? And we're going to look at a number of ways that matrix algebra can be used to solve real problems. To me, this is why linear algebra exists, right? All the stuff where it's theoretical and we're just looking at these abstract arrays of numbers and figuring out their properties, that's kind of cool from a little puzzle solving perspective. But to me, what really makes matrix algebra neat is the fact that it can be applied to real-world problems that end up being very important things to our everyday lives. And we're going to look at just a sampling of those in this episode. This is by no means all of the applications of linear algebra, but these are a few cool ones that I happen to like and that illustrate the power and give you sort of a taste and a flavor for what they can do, right? So the one we're going to look at in this opening segment is called the Leslie matrix, and this is a way of modeling population growth over time, all right? Now, a Leslie matrix is a special example of something called a Markov chain. And a Markov chain is essentially a thing that can model a system as a system evolves and basically predict future states of the system from previous states. Now, that's a lot of sort of mumbo jumbo, so let me explain what I mean by that. First of all, the word system just means sort of any complex thing that we're interested in studying. You can think of a system as being a game as it evolves when people play. You can think of a system being an economy, as the unemployment rate goes up and down and as various industries do better or worse, various companies go out of business, the stock market does things, and so on and so forth. You can think of a system being a social network as friends make friends and leave friendships and form groups, right? A system is just a complex thing that it's not obvious how it's going to behave until you study it. And a model is essentially a simplified version of a system that we design that's much, much simpler than the actual system in the real world, because if you look at the actual economy, it has 100 billion variables to it that you could never possibly get your head around. So when we make a model, we're basically selectively simplifying certain aspects of that real world system so that we can study it and say, as long as we have a reasonable approximation to how the system behaves, this simplified model, we can actually ask ourselves, what's going to happen? How is it likely to behave if it's exposed to certain conditions? What is the system behavior over time going to be? We can do that if we have a model of a system. And the key thing about a Markov chain, which is what the Leslie matrix is an example of, is that it has a certain simplifying assumption that is called the Markov property. And this is what the Markov property is. It says that the state of a system, and state is a term I'll define in a second. The Markov property says that the state of the system next year or next day, or however my time scale is that I'm simulating the behavior of the system, the state of the system in the next time period is going to be based only on its current state. Okay? The only thing that affects what the next state is going to be is what the state of the system is right now. That is called the Markov property. And when that's true, we have a Markov chain, and there's a lot of very interesting analysis we can do with it based on that initial assumption. Now, let me just mention what the state of a system is. It's kind of hard for me to explain that because it's something that I'm so used to that term now that it's hard to think of it in any other way. But here's how I think of the state of a system. Think of it as sort of like a current snapshot of the system's status right now. What is the current situation that the system is in? Another way to think of it is, if I wanted to pause a system and go do something else, go to a movie or something and come back, and then I wanted to resume that system later, the state is all the things I would have to remember, all the things I would have to record in order to resume that system's behavior at a later time. So an example would be a game, right? So I play chess with my son Johnny a lot. Let's say we're playing a chess game and I'm moving here and he's moving there and he took my piece and I took his piece and we're going like that. And then suddenly mommy says, oh guys, we have to go to Aunt Ellen's, time to put away the game. And mom and Johnny and I say, oh man, we really want to finish this game. It was a good game. What we can do is we can remember where we were in the game so that we'll be able to resume that later. Now the question is, what are all the things we'd have to remember in order to begin that game at the exact same point later on when we resume it? And the answer in chess essentially is this. We have to know what all the pieces are, where they were on the board, right? So where the white king was, where the black king was, where the white pawns were, where the black pawns were, where the white bishop is, where the black bishop is. We have to know each of those places on the board. And then the other thing we have to know is whose turn is it to go next, right? We have to remember, hey, was it Johnny's move or was it Daddy's move before we left, right? If we remember those two things and write those down somewhere, then we can put the game away and we can resume it when we get back. we don't have to remember what all the moves were to get to that state, right? Because deciding what your next move is going to be actually doesn't matter which order what thing happened, or did the queen get moved first, or who actually took your black bishop. Was it another pawn? Was it another bishop? Was it a knight? None of those things matter. All that matters is what is the state of the board right now. And based on what the state of the game is right now, what move are you going to make? And that's why chess perfectly meets the Markov property criterion, because the only thing you're going to choose your next move based on is based on what the current state of the game is, right? If you think about what the state would be for like Monopoly, it's a lot more complicated, right? If we want to tear down our Monopoly game and restart it later, we're going to have to remember how much money each person had. We're going to have to remember what token was in what space on the board. We're going to have to know what properties everybody owned and which ones have houses on them and how many houses are hotels. We're going to have to know which properties were mortgaged and which weren't. We're going to have to remember who had a get out of jail free card. We're going to have to know what order all the cards in the chance and community chess decks were. We're going to have to know whose move was it, and did they already roll once and get doubles or roll twice and get doubles. We need to know that, right? Because when we resume, it depends on who's going to go to jail or not if you end up rolling doubles 3 times. All those things are part of the state of the game that we have to capture, all right? Now, there are clearly systems where the Markov property does not apply. So let's look at an example. Let's say you're going to try to predict the weather tomorrow. You're a weatherman. Maybe it's true that today's weather is not all you need to know to predict and make a reasonable guess at tomorrow's weather. Maybe you need to know what the weather has been the last 3 or 4 days so you know which way it's trending. Or maybe if you're going to try to predict what a stock is going to do next week on the stock market, it's not enough to just know what the stock is trading at today. Maybe you need to know the past month's worth of stock prices to know whether it's likely to go up or down. So in those cases, the next state does not depend only on the current state. It depends on past states. And in that case, we don't have a Markov chain. But in this case, what we're going to look at today is going to be a Markov chain because it has the Markov property, and that is what's called a Leslie matrix. Now, what we're going to do with population modeling is this. We're going to say that at any point in time, a population of humans or of bacteria or of foxes or whatever, we'll use bunny rabbits because they're cute in our little example here. We need to know at any particular point in time, we'll say we're going to model it as 1 year at a time is what we're going to do when we move time forward in our little simulation of our rabbit population. We're going to say at any year, there are a certain number of baby rabbits, a certain number of 2-year-old rabbits, a certain number of 3-year-old rabbits, and a certain number of 4-year-old rabbits. And just for simplification, I don't know actually how long rabbits live, but we're going to say that rabbits' maximum life expectancy is 4 years. So just, if that's not true and you're a rabbit lover, please forgive me, but we're going to assume in our little simulation, just to keep things manageable size, that no rabbit lives past 4 years old, okay? So what we're going to do in our system is we're going to have something called a state vector. And the state vector in a demographic population model like we're doing is simply the population, we're going to call this state vector pop, is basically, let's say we have 67, 115, 23, 5. Let's say that's our state vector at time 0. So I'm going to say pop sub 0 here. That means what is our population at time 0? This is basically the number of baby rabbits at year 0. And when I say baby rabbits, I mean rabbits that are year 1 or less. Okay, and then this is how many 2-year-old rabbits there are. And this is how many 3-year-olds, and this is how many 4-year-olds. And of course, we don't have to keep track of anything past that because no rabbits live past that, right? So if I ask you at a certain year, what is the state of the system? What are all the things you'd have to remember if you were going to resume this rabbit colony later? The answer is, all you need to know is how many of each of the different ages the bunnies are. Because we're going to say that bunny rabbits give birth at different rates depending on how old they are. Okay, because we're going to say, rabbits reach their maximum fertility at a certain age, and maybe old age bunnies don't give birth as frequently, and babies don't give birth very often. And so that's why we need to model all the different ages here, right? Okay, so that's the state of our system, is what is the rabbit population at each of the 4 ages over time. Now, the way we're going to model that and the way we're going to predict what it is in future years is we're going to use something called a Leslie matrix, and usually we call that L. And here is the format for a Leslie matrix. We're going to say that the first row has a bunch of entries. We're going to call those F0, F1, F2, all the way to Fn. So we're going to say we're modeling n different ages, or sometimes these are known as life stages. Like if you're modeling insects and you want to go from, pupa to larva to adult or whatever that is, maybe you model each one as a different life stage. Here we're just going to say it's the age of a bunny rabbit. And the reason we use F here is because these are the fecundities. It's a really neat word, fecundities of each age. Now, if you don't know what fecundity means, it's basically a word that means the fertility, right? The propensity to produce offspring at that age, okay? And what we're going to do here is we're basically going to just be modeling females. And that's because in terms of giving birth in a population, females are the limiting factor, right? You can have one bunny rabbit that's male, and he can basically run around and fertilize everybody, right? So really, the number of babies you have doesn't have anything to do with how many males are in the population, as long as you have at least one hyperactive male that's going around and is willing to do all the fertilization tasks, right? What really matters is simply how many females there are of different ages, because once a female gets pregnant, they're going to be pregnant, and they're only going to give rise to a certain number of baby rabbits, and that can't be increased. So sort of pretend that what we're modeling here is for a mommy rabbit at a particular age, how likely it is for that potential mommy rabbit to get pregnant and to produce offspring in the next year. That's what the fecundities are. So another way to think of this is fertilities. Another way to think of that is birth rates. Fecundities just sounds cool, okay? Now, other thing we're going to have in this matrix is we're going to have S0 right here, and we're going to have S1 here. Notice I'm going down, S2, all the way down to S of n minus 1, and then we're going to have a 0 in the bottom right corner, and you'll see the reason for that madness in a minute. These S's stand for survival, and these are the survival rates of each of our ages, okay? So what this means is, and you can sort of think of this matrix as this axis is sort of the from age, and then the rows are giving you the to age. And what this is essentially doing is it's saying, what is the survival rate from being a baby to being year 2, right? Because this is column 1 and this is row 2. And then this S1 is saying, what is the survival rate if you are going from a 2-year rabbit to a 3-year rabbit? So each of these S's is going to be between 0 and 1. So all of the S sub K's are going to be between 0 and 1. If it's a 1, that means that a rabbit of that age has a 100% chance of surviving to the next age. If it's 0, it means that all rabbits of that age are going to die, which does happen at the final year here, right? So all the rest of the entries here, believe it or not, are 0 and must be 0 for this to be a valid Leslie matrix. And all of these must be 0, okay? So all of the entries except for the F's on the top row and the S's on the first sub-diagonal, that's what this is called. So this is the first row, obviously. And this is the first so-called sub-diagonal, because remember, the main diagonal of a matrix is this guy here, right? Which doesn't turn out to be important for Leslie matrices. For Leslie matrices, what we care about is this sub-diagonal here, which is the one right below. And you'll notice that we only have n minus 1 non-zero entries here, whereas we have n here, right? And that's because we're saying that once you are a 4-year-old, say, or in general, once you are an n-year-old, you have no probability of going on to the next age. So we don't even have to keep a number for that, right? All we need to do is say, what's the probability that a baby will reach year 1? What's the probability a 1-year-old will reach year 2, etc., right? I think of this as when you have kids and your kid is really, doing something annoying, right? Like he's not cleaning his room. And you say, hey, little Petey, how old are you? And he says, I'm 4. And you say, do you want to live to be 5? Because if so, you better clean your room, right? Maybe your parents said that to you at some point. So it's the same idea, right? You have lived to age 4. Now, what's the probability you are then going to continue to reach age 5, right? Maybe that's dependent on some external factor, like whether you decide to clean your room or obey dad or whatever, right? So it's the same sort of thing here. If you are a 5-year-old bunny, what's the probability you survive to year 6? Or if you are a 9-year-old human, what's the probability you survive to year 10? That is what those survivability rates are, right? Now, you can see why everything else is 0, I think, right? Why are these all 0 and these are 0? Well, that's because if you are a baby rabbit, so if you're going from age 1 here, there's only 2 possibilities. Either you survive and become a 2-year-old rabbit, or you die, right? You can't become a baby rabbit and the next year jump to be a 3-year-old rabbit. If you're a 4-year-old rabbit right now, you can't become a 2-year-old rabbit next year, right? There's only one way to go, and that's from age 1 to 2, age 2 to 3, age 3 to 4, age 4 to 5, age 5 to 6, etc., and then you die. So the reason this first row can be all non-zero, and by the way, there can be zeros up here, it's just that they don't have to be. But the reason the first row can be all non-zero is because, in general, any age rabbit or bacteria or whatever can give birth to other babies. And then the rest of these things here only are non-zero on the diagonal because your age only goes up, and it goes up 1 year at a time, right? Okay, so now, here's the big deal. The big deal is, if we have our population vector at a particular time, like let's say we're starting off our bunny population with 10 babies and nobody else, right? We're going to take 10 babies, put them in a little meadow and see how they do. Let's take a Leslie matrix here. So I'm going to make a real life one as our example. I'm going to say this is 0.1, 0.5, 0.50, 1, 0, 0, 0, 0.500, 0.50. So just take this as our first example here, right? So first convince yourself that this is in fact a valid Leslie matrix. Okay, I've got zeros all the places I should. I have a 0 here too. I don't have to, but in this particular example I do. Now think about what this Leslie matrix means, right? This here, this 0.1, means that baby rabbits only very rarely give birth to more baby rabbits the next year, because maybe they haven't hit their maximum fertility yet. And maybe only the really advanced, maturing, sort of the upper end of the bell curve baby rabbits are able to produce new baby rabbits the next year. Most of the time that doesn't happen. And that 0.1 essentially can be translated like this. It means that for every 10 current baby rabbits, there will be 1 new baby next year. That's what that 0.1 means. So only a 1/10 chance is there for a current baby rabbit to give birth to a new baby rabbit, right? Only 10% of those result in new baby rabbits. As opposed to this, that means, wow, those 2-year-old mamas are really fertile, right? Because that means for every 2 current 2-year-olds, there will be 1 new baby next year. So, if I've got 50 2-year-old rabbits, I'm going to have 25 babies from them in the next time period. And that is also true for 3-year-olds. And then here we're saying that once you're a 4-year-old rabbit, you are infertile. You cannot give birth. And that's what that 0 there means. Okay? Now, what does this mean? This means babies automatically survive until year 2. That's what that 1 means right there. This 0.5 means only half of 2-year-olds live to become 3-year-olds. And that is also true of the, it's a 0.5. This is also true of 3-year-olds becoming 4-year-olds, right? And so these are the conditions of my system here. Now, the question is, if I know, let me sort of do a clean screen here. So here's our L. We've got 0.1, 0.5, 0.50. We've got 1, 0, 0, 0. We've got 0, 0.500, and we've got 0, 0.50. Okay, so what I'm going to do, if I say that I've got my pop0 vector, which is the populations at time 0, and that was 10 babies and nobody else, how do I compute the population in year 1 year from the beginning, do you ask? And the answer is matrix vector multiplication. Whoa, no way. Yeah. Because look at how this works. This row right here is saying for every baby rabbit, how many new babies are there going to be. For every 2-year-old rabbit, how many new babies are there going to be. For every 3-year-old rabbit, how many new babies are there going to be. For every 4-year-old rabbit, how many new babies are there going to be. So all I got to do is dot product that with the current population of all those ages. And in this case, I'm going to get 1, right? Because 10 times 0.1 is 1, and then the rest are all zeros. So that means that these 10 baby rabbits are going to give rise to one baby rabbit in the next time period. Okay? Now, those 10 baby rabbits are all going to grow up to be 2-year-old rabbits. Because we have a 1 here. And then this dot producted with that gives us 0. And this dot producted with that gives us 0. So in the year number 1, which is 1 year after our simulation started, we now have 1 baby and 10 2-year-olds and nobody else. And then what do we do to get time 2? Well, we just do that again. We take 1, 10, 0, 0 as our state vector, and we multiply the Leslie matrix by it, and we get the vector for year 2. And that is going to be, if you multiply this out, so this is where it gets a little funky because we're going to have fractions here, and I know you've never seen 0.1 of a rabbit rolling around, right? And that's actually a decision we have to make. We have to decide, are we going to basically be modeling the long-term expected probabilities of this thing, or are we going to round each one of our answers to an even number of rabbits in order to get a real rabbit population, right? So for now, we're just going to not truncate those, and we'll look at what that does later. But let's not truncate those and say 0.1 here times 10 is going to be, I'm sorry, my bad. I was looking at the wrong thing. We're taking the dot product of that with our pop1 vector, right? So 0.1 times 1 is 0.1. So one way to look at that is that on average, you're going to have 1/10 of a rabbit being born to this one baby rabbit. So one way to look at that is, well, there's a 10% chance that we do get a baby out of that baby. There's a 90% chance we don't. So on average, sort of the expected value is going to be 0.1, okay? And then we're going to have this 0.5 times 10, and that's going to end up giving us 5. So the total there is 5.1 babies on average that we're going to get in year number 2. And then we're going to get a 1 here because this one baby does grow up to be a cowboy and becomes a 2-year-old. And then we're going to have a 5 here, right? Because of these 10 rabbits here, only half of them survive to be age 3. And then we get nobody in age 4 yet. That's pop 2. And then if we multiply L by this guy, we can get pop 3. And if you work that out just to satisfy the curious, that turns out to be 3.51 and 5.1 and 0.5 and 2.5. So now we finally have some 4-year-olds, okay? And that continues and continues and continues. And in general, if I multiply L by itself t times, and then multiply by my initial population vector, that is going to give me the population at time t. Okay? So L to the t, multiplying L by itself, t times my initial population, gives me the population at time t. And that is a powerful thing. Because that means once I know the fecundities and the survival rates, which I can get from a biologist, right? Somebody who studies rabbits can do various experiments and data collection and say, we've determined that the fertility rate of rabbits that are 3 years old is such and such, and we know that, in this particular population, they, mature at a certain rate and they die at a certain rate. Once they give us those things, then we're in math land, and we say, great, thanks, biologist. Now that you've given us those survival rates and those fecundity rates, I can now project outwards what is your rabbit population going to look like in 10 years. What's your rabbit population going to look like in 50 years or 100 or 1,000? What's the long-term behavior of your rabbit population? That can be determined simply by multiplying again and again and again by the Leslie matrix and giving it every year. And of course, we're not going to do that by hand. We're going to do it by computer. So let's do that. Let me start with R here, but if you're doing the Python track, you can fast forward at this point to the point in the video where the Python part starts. Let's start with R. In R, notice I have this matrix here, and I'm going to start it off like this. In fact, let's just take a look at what that looks like by pasting that in here. So this is my Leslie matrix, and the first thing you should do is satisfy yourself that this is a valid Leslie matrix. It has zeros all the places it needs to, and it does. The first row has the fecundities, and it looks like in this particular one I have different numbers here. We're again saying that babies don't often give birth to other babies, and that, ages 2 and 3 are pretty good. Ages 4 is huge though, right? So age 4 in this particular model, we're saying that those are the most fertile actually, right? Before they die, they give birth to other babies at a rate of 1 baby per potential mother. We're also saying the survival rates are good here, right? So 90% of the babies survive to year 2. 90% of the 2-year-olds survive to year 3. 90% of the 3-year-olds survive to year 4, all right? Now, what I've done in this program here is after I make my Leslie matrix, I'm going to make a whole matrix of populations. And the reason I'm making a whole matrix is because I want to keep pop 0 in the first column, and pop 1 in the second column, and pop 3 in the third column, so that I can plot it all at the end. Okay? So instead of just writing over our pop vector, I'm going to be continually adding a new column, a new column, a new column to track the population demographics over time. So the first thing I do is I say, let's set the first column to be 10, 0, 0, 0. So we're going to, again, start with 10 babies and nobody else. And remember this notation here, I'm saying, I want to set all the rows, column number 1, to be this vector of 4 entries. And then we have our main loop, and notice the way this is working. I'm saying I'm going to let I go 2, 3, 4, 5, 6, all the way to 40, right? So the first thing I do is I say, well, set pops column number 2 to be the Leslie matrix times pops in column number 1. And then let pops of column number 3 be equal to the Leslie matrix times pops of column number 2. So I keep computing one column from the previous one by multiplying the Leslie matrix by it. And then at the end, I'm simply going to do my plot. And you may not have seen this function before, lines. It's really the same as points, except instead of drawing points, it draws lines, which is a little bit easier on the eyes. And I'm going to plot the babies in blue, the 2-year-olds in red, the 3-year-olds in green, the 4-year-olds in black on one big plot, and we're going to see how it works. Now, I'm going to press run here, but before I do, ask yourself this question. Given this Leslie matrix, can you figure out what's going to happen? Do you think this rabbit population is going to survive, or is it going to go extinct, or is it going to have a lot of babies, or is it going to have a lot of adults? I can't tell just by looking. That's why I use computers. So I press source, and here's what I get. Exponential growth. These particular numbers give rise to an unbounded population growth. Rabbits are taking over the world. Okay? And in fact, in just 40 years, I have thousands of rabbits from my initial population of 10 babies. And you'll notice that the babies are gaining on the 2-year-olds, who are gaining on the 3-year-olds, who are gaining on the 4-year-olds. So my population is getting younger over time. Okay? That's what's happening in this particular numbers. Now, I can play with these numbers and say, what if I take this 0.9, and I'm going to jack this down to 0.3. Now, what does that mean? Well, that means that although baby rabbits very often survive to be 2-year-olds, and although 3-year-old rabbits very often survive to be 4-year-olds, turns out that 2-year-old rabbits have a hard time surviving to age 3. And that's because maybe they're the hunting rabbits. They're out hunting, lettuce or whatever, for the tribe. And they get killed by farmers who are, swatting them or whatever. And so, that's really the death age. Once you've made it to year 3, then you kind of kick back in old age and just give birth to more babies. And so your, probability of survival is very high then. But in this age, it's bad. Now, what do you think that would do to the population? We'll find out by running it. And it turns out, boom, now our population goes extinct. There's a lot of wild variation here at the beginning as the population settles down from lots of babies to hardly any babies to more to less to blah, blah, blah. But the long-term behavior of this thing is to go extinct. Now, we can play with this and say, well, gosh, what happens if we rise this up to, 0.5? What's that going to do? Is that good enough to let it survive? And the answer is yes. It's not nearly taking off at the rate that the other one did, but clearly this is not going to go extinct. In fact, it's going to grow. And in fact, here it looks like we have an even younger population than we did, because now the babies and the 2-year-olds really are the lion's share of the whole rabbit population, right? And we can play with this and say, well, what if we jack it down to 0.4? Is that enough to keep our rabbit population alive? Turns out no. It's decaying slower, but it's still decaying beyond what it was there before, right? So all these things allow us to learn about the long-term behavior of the thing. If I wanted to say, you know, instead of leaving fractional rabbits, right, because that's what I see now if I look at my pops matrix, I see this is what's happened over time, and I keep getting, you know, fractional rabbits here. I could say, well, let's round this thing so that every time I, you know, get to a certain rabbit thing, I'm rounding to an even number of rabbits. We notice this sort of thing right now. It jerks to exact even multiples. And in fact, this time it shows that, you know, if that happens, we're going to end up getting an exactly stable population that's very fragile, because at any moment, if one rabbit dies, this whole thing's going to collapse. But that's the behavior you get if you get rid of the fractional rabbits, okay? So that is a Leslie matrix, and that is a very simple but very effective and commonly used way of modeling a population's demographics over time. Interestingly, we will learn in a couple episodes that if you examine that Leslie matrix and you compute, get this, the eigenvalues of it, that those eigenvalues are going to tell you the long-term growth rate, whether it grows or shrinks and by how much. And the eigenvector that goes with the largest eigenvalue is going to tell you what the population demographics are going to be over time. Is it going to be mostly babies, mostly adults, even of each? Is there going to be a baby boom in the middle, right, like we're having in our country right now? All those things are revealed by looking at the eigenvalues of the matrix, so I will leave you hanging on that. All right? Now, let's do the same thing in Python. Python here, so I've got my Leslie matrix here, and what I'm going to do is I'm going to start it at this particular value. Oops. And let's just look at what that looks like first by copying and pasting it over here. So here's my L, and the first thing you ought to do is convince yourself that this is a legit Leslie matrix. It has zeros everywhere it needs to, and it does. It's different numbers than the one we had earlier. So right now I've got, you know, fecundity rates of 0.1, 0.4, 0.5, and then 1. So wow, it looks like here I've got my old rabbits really being fertile. They're actually giving birth to new baby rabbits at a rate of 1 baby per potential mother. And then the survival rates are quite high. I've got 0.9 probability of a baby surviving to 2 years, and a 0.9 probability of a 2-year-old surviving to 3, and a 0.9 of surviving to old age. So it's different numbers, but that's what my Leslie matrix we're going to start out with here. Now, what I'm doing here is I'm making a matrix of all zeros to represent the populations. So instead of simply writing over the population vector each time, I'm going to keep each population vector in a column of a vector. And that is so I can plot them all at the end. So what I'm going to do is I'm going to say, let's make pop 0 be the first column of this pops vector, and pop 1 be the second column of this pops vector, all the way through 40 years worth of simulation. And then what I'm going to do to start off is I'm going to set my first column to be this 10, 0, 0, 0 thing. So again, we'll start with 10 babies, right? So remember this syntax here, colon, comma, 0 means set all the rows of column 0 to be equal to this 10, 0, 0, 0 thing. So we started off with that. And then the main loop, here's how this works. I'm going to let I go from 1 all the way to 39. And each time I'm going to say, make one vector of the population matrix be L times the previous column. So I'm going to say, make column 1 be equal to L dot producted with the column 0. And then make column 2 be dot producted with column 1, make column 3 be dot producted with column 2, etc., so that I build this entire matrix, and then I'm going to plot them all at the end. I'm going to plot the babies in blue, I'm going to plot the 2-year-olds in red, I'm going to plot the 3-year-olds in green, and the 4-year-olds in black. That's what those letters stand for there. Okay? So, you might ask yourself, before I press the green play button here, what's going to happen? Would you predict that this population survives or it goes extinct, or how are the various ages going to work out? I can't figure that out by eyeballing it. But if I press play here and run it, we will see that we get exponential runaway growth. So notice I've got 1,200 plus rabbits after just 40 years rather. And so these numbers give rise to rabbits taking over the world, basically, right? And notice, by the way, that the overall bunny population is getting younger, because the babies are gaining on the 2-year-olds, who are gaining on the 3-year-olds, who are gaining on the 4-year-olds. So over time, you know, my percentage here looks like it's getting more baby-ish. Now what we can do is play with these numbers and see the effect. So I'm going to go here to this 0.9, and I'm going to change this. I'm going to jack this all the way down to 0.3. So this would indicate that although babies almost always survive to be age 2, and although 3-year-olds almost always survive to be age 4, nevertheless 2-year-olds often die and don't make it to age 3. So maybe that's because the 2-year-olds of the population are hunters. They're out hunting lettuce, and they're getting caught more often by farmers who are getting them in traps or shooting them or whatever. And so maybe that's the age at which it's very critical, and most rabbits die there. Once you've made it to age 3, then you have a 90% chance of making it all the way to old age and being your super fertile self. But in that case, we're going to say that this particular age range has a problem surviving. Now, one thing you might ask is, what would that do to the overall population trend? And I'll kill the suspense by running it and showing that, wow, look at that. This thing now goes extinct. So simply not allowing the 3-year-olds to make it to age 4 very quickly ends up killing this whole population, which isn't super surprising because the 4-year-olds were the most fertile here, right? Now we might say, well, gosh, how far does that go? If I jack this up to 0.5 and I say they can survive half of them from age 3 to age 4, is that enough to keep the population going? And the answer is yes. And we see now that even though it's not going nearly as fast as it was before when we had a 0.9 there, nevertheless, we are not going extinct and we are going to continue to grow. And in fact, it looks like here we have an even stronger, younger population. In fact, a greater percentage of the population is young than was old here, right? So fun fact there. And then we might say, is there a critical value if we get on a 0.4? Is that enough to survive our species? And the answer is no. We are going to go extinct at 0.4, right? Even though it's going extinct slower than it was at 0.3. Nevertheless, it looks like the magic value is I have to have at least 0.5 or so of my 3-year-old population surviving in order to keep my rabbit population alive over time. Now, if you were bothered by the fractional rabbit thing, right, so if I look at my pops, I see, all these values here, and, they're clearly, fractions of a rabbit. So one thing we could do is say, you know what, instead of doing that, let's round. So remember, our round underscore function is how we did that. So every time when I set the population vector, let's round what I had here. Now what we're going to get is this effect. So it looks like if we're rounding to an even number of rabbits, we actually barely survive here with number 4. We have a very delicate balance because if even one of these rabbits dies, the whole thing is going to crash. But this thing now is evening out to all integer number of rabbits, and so that's the effect there. Again, normally if we're sort of modeling this as a probability type thing, we're not going to do that. We're going to say, well, say 0.6 rabbits basically means there's a 60% chance we have a rabbit, and a 40% chance we don't, and so we can kind of consider that long-term average as 0.6 of a rabbit. All right? Very effective, very commonly used, simple but very useful way of modeling a population over time and what its characteristics are going to be. Interestingly, as we'll discover in a couple episodes, we can compute what the long-term growth rate of the population is going to be and what the long-term demographic makeup of the population is going to be by looking at the eigenvalues of the Leslie matrix. And it turns out that if we compute the eigenvalues of the Leslie matrix and then the eigenvector that goes with the largest eigenvalue, that tells you overall what is the long-term growth rate going to be. Is it going to grow or is it going to shrink, and by how much? And we're going to get the long-term population makeup. Is it going to be young? Is it going to be old for the population, etc. Simply by doing that computation. That's one of the magic things about linear algebra that becomes apparent once you use eigenanalysis to peer deeply into the structure of the matrix. So I'll leave you hanging there. Stay tuned for that.